This is track 3 malware. The talk is Hardware Backdooring is Practical by Jonathan Broussard.
Thank you, mate. Thank you for coming. Before we start, I will ask you to give a big applause to all the goons, the staff, the organizers. It's massive work, they've not been sleeping. Thank you for them. All right, so we're going to talk a bit about backdooring hardware. Obviously, we had Black Hat and stuff, so we're not terrorists. Interestingly, the source code is already public, because most of the malware is built on top of open source. The main problem really is that the PC architecture is plagued by legacy. It should not be a surprise to most of you. But we're going to see that it's actually plagued to an extent that I believe it's not possible to do security on the PC really. There is a need to discuss these problems. I don't have a magic solution, but feel free to contribute. And one of the points of why doing a talk like this, I believe this is slightly better. We will see why over existing work. So we will start by explaining, if I was to design a backdoor, which is something I don't usually do, I would like it to be epic. I want to do it once. So we'll start by designing a scope of work on what would be the perfect backdoor. Then I will explain you a bit of architecture, of Intel architecture. We'll review the state of the art of rootkitting, BIOS kitting, ROM kitting, and then introduce you to the new work I've been developing. All right, so the typical one my slide. So I'm a security researcher. I do a bit of pen test because they keep promising me that the next month I'm going to do mainframes and stuff, and it never happens. I studied assembly about 15 years ago. It was my first language. So I think the first language you will learn is actually super important for the way you see computers. And I studied by running disassemblies of viruses and stuff. I had no idea what's difficult, so you don't consider it as such. I've been a speaker at a few conferences. If you would like to speak yourself, we're actually organizing a conference in Paris, Hack It to Argosum, which is mostly around reverse engineering and low-level stuff. Feel free to submit. Well, that's it. And okay, my English is not quite perfect, right? First off, I'm French, which is quite a handicap when it comes to language. Then I learned English in India. And to make things really perfect, I live in Australia. So if you don't understand what I'm saying, maybe it's not just you. Feel free to ask me to reformulate. All right, a bit of fun to start and see why it's interesting. All right, so could a state like China, for instance, is very much in the air, backdoor computers. So this was this terrific report prepared for the US Senate, and they actually realized, after 30 years, that most computers nowadays are actually built in China. Even if your computer is actually designed in Western countries, the modules which are assembled all come from China. So it magnifies definitely the risk of someone backdooring. A bit more fun, and it's the last bullshit slide, I promise. So if you read the news lately, you find claims such as 80% of the world communication are backdoored by China. China is backdooring 80% of the telecoms. In France, it was interesting last week. Basically, they realized that the whole core network of France is built out of ZTE hardware. And they thought that, somehow this was not quite appropriate. And they choose to default to Alcatel-Lucent, which is, the main problem from a European point of view is that really we don't have anybody building core routers and stuff like that. Alcatel is Franco-American, but the hardware is still very much built in China. All right, that's it. So let's switch a bit to the architecture. Let me introduce you to the problem. Here is the Intel architecture. So basically, it has a few layers. If we go from the slower peripherals, so ISR was like the first turf design in the original specs of the IBM PC in 1981. So all those peripherals have one characteristic in common. They are slow as shit. So you have the mouse, the floppy, the keyboard, and that's pretty much it. The South Bridge contains most of the peripherals, like anything which is like, you know, your typical Ethernet card, your CD-ROM, your sound card, whatever, should be connected to the South Bridge. Then you have the North Bridge. Basically, the closer you get to the CPU, the faster it gets. So the North Bridge typically is connected to peripherals which are much faster, like extended PCI, which is used for Gigabit Ethernet, SAN communication, video. And then you have like the proper CPU. So one thing which you can notice is that TPM is actually connected very low inside the chain, right? We'll get back to this later. The other problem, I mean the main big legacy problem, which is a bit unexpected, is that at each layer, on every peripheral, you have a bit of firmware, which can actually control any other firmware of the same layer. So for instance, you could flash a firmware on your CD-ROM, and it could control your network card, which is a bit unexpected. And there's really no way to fix it. It's like the standard is like this. And we're going to see that this leads to some problems. Any questions so far? Yep.
What is FSB?
FSB, it's a fast something bridge. Exactly. I just wondered if you guys were following. So let's talk a bit about the state of the art. The idea of getting early execution is really not new. Like the first IBM PC virus, Brain, which was allegedly built in Pakistan, was targeting himself the masterboard record. In the 80s and 90s, like virtually every virus was acting this way. Then, with the appearance of internet, people started to switch to like higher languages, like, you know, to spread via email and stuff like that, which is a bit uneasy if you start very low level. So people started to spread like, you know, VBS malware and stuff like that. Then in 2007, so John Nisman from NGS resurrected sort of the concept of backdooring. So not exactly the BIOS, but the EFI, which is the standard which was before unified EFI, and which is now deprecated. He inspired his work a lot from the work from EI, Bootroot, which was a bootkit. So it's not exactly a backdoor, but the idea was like to subvert the kernel by patching it on the fly to gain higher privileges. Then an amazing work from the guys from Core Security in 2009. They did it the hard way. They said, all right, like, let's forget about the masterboard record. You know, if people change their hard drive or reinstall their operating system, you don't keep execution anymore. And they did it the hard way because they took a firmware from a BIOS, the Howard firmware. They identified the checkrooming routine. They patched it to introduce interesting functions, and they patched back the checksumming. They compensated the checksumming of this firmware. So it was really the first BIOS kit known. Then a bunch of people worked on bootkiting. There again, not exactly from a backdooring perspective, but more to elevate privileges. Everybody's familiar with what's a bootkit? Too easy? Okay. So the best commercial bootkit you can find these days is the one from Banya. It's called Coreboot, and it's pretty simple. It works for every version of Windows, 32 and 64-bit. It's pretty decent penetration testing tool. Like if you need to elevate privileges, assuming you can boot the computer, you boot on a floppy or a CD-ROM, and it's going to patch on the fly the kernel so that you don't need, you can authenticate using any password with the administrative account. Anybody has seen Snare in the morning? Yep. Was it good? So his work is pretty related because he's been working on the unified EFI, which is like what's used mostly by Apple, and is upcoming also for Intel. And so like it's pretty complementary. The idea that it's not entirely different, it's still very much a BIOS backend actually to detect the hardware and stuff, your peripherals. But instead of having an interrupt vector table, you're using another set of API to interact with the hardware when you're trying to unpack a kernel in memory. All right, let's go for the meat. Okay, so let's say we want to do the super cool backdoor of the year. We want it persistent, like obviously not just persistent between reboots, but persistent as in even if you remove the hard drive and change it, even if you reinstall the operating system, even if somehow like you remove peripherals and you put other peripherals, or even if you actually flash the BIOS, we still want to be there. This is what I define as persistent. We want to be stealth. So I think this is pretty interesting. We're going to try to have zero hostile code on the machine, which leaves zero attack surface for an antivirus, if you think from a malware perspective. Ideally, it should be portable, so like not targeting any operating system. If you want the perfect backdoor, come on, we'd like remote access. We'd like to be capable of remote updates, even if we're talking about firmware stuff. If you want a nation-state quality backdoor, think Flames, Stuxnet, we'd like two things. Plausible deniability, which is basically saying, oh no, it's a mistake, like it wasn't a backdoor. And non-attribution, which is basically, oh no, it wasn't me. Usually it's like, it wasn't me, it was China. Ideally, we'd like to cross network parameters. If we are to backdoor proper corporations and stuff, it's very likely that they will have authentication firewalls, they will have IDS, IPS, whatnot. So like, we'd like to get rid of all this problem at all. We'd like to have some degree of redundancy. There again, if say we want to infect the CD-ROM driver, the CD-ROM firmware, if for some reason the user decides to remove the CD-ROM and put another one, not the proper disk, but like remove the physical peripheral and put another one, we still want to be there. So we need some degree of redundancy. And needless to say, we don't want to be detected by antiviruses. Who works for an antivirus company? All right, Andrew, yeah. You do, actually. All right, so let's go to the design thing. So Rakshasa is built on top of free software. Who's familiar with Coreboot, for instance? Coreboot is awesome. It used to be called Linux BIOS. It's like, a BIOS is basically comprised of two things. You have the back end of the BIOS, which is responsible for doing the BIOS pulse and discovering all the peripherals. It's basically the first piece of software which is executed in memory on your computer. So like it's responsible for finding critical things such as the RAM, such as the hard drive, and all the other peripherals. Then the other half of a BIOS is like the front end, if you will. In the Coreboot language, they call it a payload. And I've been using CBIOS, but there are a few other alternatives with like better GUIs and stuff. The idea is that CBIOS will do only one thing. It's initializing an interrupt vector table so that you can actually program the hardware. IPXE is an extension of, it's an implementation of PXE and a massive extension of it. PXE is basically a standard which has been defined by Intel and IBM, I think, to allow remote booting. And it was using DHCP and TFTP. That's not really good enough for me. If I want the backdoor of the century, I don't want to be limited to TFTP. So IPXE provides massive network stacks at firmware layer. You have like a full TCP IP stack, obviously UDP, but you also have like upper layers. You can do FTP, you can do HTTP, you can do HTTPS, which is going to be interesting for us. And then we have a set of payloads, and I'll get back to this later. So the good thing about using free software, when you think about it, apart from portability, because Coreboot is working with 230 motherboards currently, I'd like to remind you that the state of the art is to infect one BIOS. It's the job from core security. All right, so then think about it. 230 motherboards. And I did not do the job. They deserve all the credit. In terms of non-attribution, if you think about it, most malware today, to date, contain like 99% of custom code. It's basically built from scratch. So it's super expensive. People do code reuse between releases, like, Dooku is borrowing from Stuxnet and whatnot, which in terms of non-attribution is not so great. If you're using open source software, you can definitely say, it wasn't me, it was public on the internet. So this clause is a given. And it's pretty cheap development for the result. Also, if you're using only open source stuff, which is legit, and they are legitimate projects using Coreboot, CBIOS, or IPXE, it's going to be very hard for an antivirus to distinguish a malicious version of Coreboot from a legit one. The only thing I did really on Coreboot was, with a few twists, was to patch the definition of printf to get rid of the, this is Coreboot, blah, blah, blah. From an antivirus perspective, the attack surface to detect this code as malicious is basically 0. All right, so let's go to how it works. So the idea is to infect multiple firmware inside the computer. The first one, which is like the obvious, you want to infect is the BIOS, because it's the first one to get executed. But basically, when the BIOS does its BIOS post, it executes every firmware to do initialization. And if we infect, for instance, the PCI-ROM of the CD-ROM, we get as early execution pretty much as the BIOS. We get executed on 86 real mode, because this is the mode the CPU starts on. And we are the only one in RAM. This mode does not support multitasking, right? So like you have access to everything in terms of resources. But maybe if the IOMMU is in place and is decent, maybe you can now write to some portions of memory. So the idea is like we're gonna flash the BIOS and we're gonna flash other PCI ROMs. Like I said previously, we can very well use IPXE, which is a network firmware, and flash a CD-ROM with this firmware. And it's actually very much going to work. So this is what's going to provide us redundancy. And even if the BIOS is somewhat disinfected, for instance, because the user does its proper maintenance and decided to flash his BIOS to do like CPU updates or whatever, we still have early execution and we can patch the BIOS back. I'll get back to this. What we want to do really, eventually, is boot a bootkit from the network. Instead of having it on the file system, but even on the BIOS or firmware, like it would be much better to have zero style code on the computer and fetch it at boot time every time. So I told you about breaching the network perimeter to avoid detection, and basically it's very hard to at this very early stage to steal the credentials of a user. If the hard drive is encrypted or whatever, stealing the credentials to access an authentication proxy is going to be pretty tough. So we're going to get rid of this problem entirely. We're going to try to go primarily over Wi-Fi. Because there again, even if the company has like massive layers of IDS, IPS, etc., if you use Wi-Fi and with some decent encryption, they're very unlikely to actually detect that you're doing any kind of connection at all or exfiltrating data. A good thing with IPXC is actually it can fail and default to other settings. So what I do in my backdoor is trying to first boot over Wi-Fi or WiMAX if it's available. WiMAX is even better because it's faster. If for some reason there is no Wi-Fi on the current computer, then we're going to try to default to DHCP. If DHCP is not there, we're going to try to default to a static IP. And if you cannot connect using a static IP, basically the stuff is like, well, pretty unlikely to have any kind of network connection, right? If everything else failed. Okay, and we're going to show that, we're going to see that it will be possible to basically reflash a firmware later on. Any questions so far? Too easy. All right, so we said being generic is better because not only, if you're not system dependent, operating system dependent, upcoming versions of whatever operating system you're using, or if the user is using a very exotic operating system, well, you'll still be able to get execution. So I'm going to show you how we can remove the NX bit. Everybody's familiar with this concept? Non-executable bit. I'm going to show you how to make the mapping, every mapping in memory writable in ring 0 from a bootkit or from the BIOS itself. We're going to see how to downgrade the security of the CPU. Basically, microcode updates are usually pushed in the BIOS itself. They got to be pushed early, and you need massive privileges to do them, obviously. So if you're not familiar with this concept, basically when vendors, Intel or AMD, have a problem with their CPUs, instead of changing your CPU, they allow you to push a signed microcode update, which is going to reprogram the CPU and compensate the physical problem which was there in the first place. So clearly this is signed, using proper asymmetric cryptography. And the idea that if we get rid of those protections, which are usually pushed at the BIOS layer, we're going to downgrade the security of the CPU entirely. Some of those bugs are actually exploitable. We're going to talk a bit about SMM, which is really the patch mode or ring -2 for Intel-like CPUs. I will not enter into the details, but basically Loïc Duflo in 2006 and 2007 at Consequest presented an attack. So SMM stands for System Management Mode. It's basically possible to switch to this super elite mode, which is better than ring 0, by triggering what's called an SME. You can do it from userland, but there are, and the big problem is that the SMI handler is basically overlapping with other content in memory, typically your video card, video frame buffer. So BSDmin showed a generic exploit for it in FRAC. So if we manage to get rid of those SMM protections, we get a local root. And it's a given. It's going to work whatever operating system you're using because it's a physical problem. We're going to talk a bit about disabling address space layer randomization and a bit of bootkitting. The bootkitting part has been provided by Piotr Bania. I actually asked him, like, can you help? And he helped, which is cool. Okay, so how do you remove the NX bit? This is getting a bit gory, stay with me. Okay, it's, first off, every CPU doesn't have it. It's a model-specific register. So assuming you have the NX bit, the AMD 64 manual state that there is a specific bit in the EFER register, which is also a model-specific register. And if you flip this bit, you disable or you enable non-execution. So the fact of marking, I mean, historically, everything which was mapped in memory used to be executable, which is a terrible idea from an exploitation perspective. So they introduced this bit with the K6 generation in '97. So the idea is like, we'd like very much to get rid of this stuff. So we can do it this way, assuming so I get back to how we get to bootkit execution, but assuming we can launch a bootkit, basically the idea is to use the CPU ID instruction. If you don't have the CPU ID instruction, your CPU is older than '97. So I will assume that it's all right, I don't care. So first off, we query like, which is the higher function supported by the CPU ID instruction. The function is always provided in EAX. If we have something which is lower than 2000 something 1, then it's not going to be good enough, but there again your CPU is super old. If we do have this instruction, we query what are the processor information and feature bits, so which are processor specific, which you actually do support. And the one we're interested on is the bit 20 in EDX. CPU ID returns, I mean, the output of CPU ID is basically two registers, it's ECX and EDX. And assuming you actually do have the NX bit, we're just gonna flip the bit on EAX. So the whole thing is like the EFER register, which is actually C000080. So we're gonna read this MSR into EAX. You don't do MOVs with model-specific registers. You do this weird thing, RDMSR, right? So this is gonna load the content of the EFER register into EAX. We test if the 11th bit is there, the one corresponding to NX, and we reset it and write back to the register. So the net effect is to disable NX. Any question? Too easy. Okay. This is something which is actually, I mean, the fact of changing permissions in ring 0 is actually something pretty common. If you saw Dan Rosenberg's exploit last year, his remote kernel exploit on X25, he was actually using a trick like this. So the idea there again, by the manual, the Intel manuals, you have a specific bit which, if you flip, makes everything which used to be read-only in memory executable again. Writable again, which is a super massive cool feature. So it's a bit in CR0. It's the 16th bit of CR0, the control register 0. So like, it's very straightforward. Like, you just read CR0 into EAX, you mask the bit 16 and you write it back. And it's the same thing in 64-bit. The thing is, in 64-bit, the first 32 bits are always 0 anyway, in CR0. otherwise you get a general protection fault, says the manuals. So removing the CPU updates. So Coreboot actually does provide the capability of patching your CPU on the fly using CPU Microsoft updates. For the perspective of my backdoor, all I had to do was really to delete all the microcodes, and that's it. We got rid of it. So the SMM thing is a bit touchy. Basically, you have two bits, dopen and dlock, which are to be taken into account. The idea that when the dlock bit is set, you cannot use SMM anymore, ever. And this dirty fix is supposed to be provided by the BIOS. The specifications say that the BIOS can use the dopen function to initialize SMM, and then use the dlock to lock down SMM space. The problem, of course, is that you don't have to. So the only thing, Coreboot does not support it. So like, if you want to get rid of SMM protection, you just install Coreboot and use a super shellcode, or which does nothing. Any question? Yeah?
What's to prevent the operating system from not doing all of this as soon as it boots?
Because they don't have sufficient privileges. It has to be like super early.
Well, I can see that for the SNF mode, but as far as writing the MSR and changing that to the CR,
Oh yeah.
absolutely.
Writing to MSR, yeah, definitely. So like, what's your question? Like, if I remove it, can they put it back?
Well, I guess the question is, why would you expect, operating system people to turn around and, for instance, if they're not already writing the bits of the MSR and CR0, or, in this case, for instance, you're just saving the log.
Okay, I shouldn't have skipped the definition of a bootkit. Basically, a bootkit is... All right, let's step back. Let's assume I get execution on the BIOS magically. We'll explain how. And I'm fetching a bootkit from the internet. All bootkits work the same way. They hijack interruption 13, which is the one which is used for every disk access. All right. Remember that when you boot a computer, you have no such thing as a libc or a kernel. The only API, so to speak, is the interrupt vector table. So if you hook interruption 13, you're hooking system-wide access to the disk. And somehow the masterboard record, which is loaded at 7C00 in memory by interruption 19 when you're trying to boot, is going to use somehow, the masterboard record is going to try, its whole point is basically to try to take a kernel from the disk and unpack it in memory, right? To do this, it has to access the disk. So if I'm owning interruption 13, I can make sure that during the unpacking, I can hook the reading from the sector is going to read the kernel from, right? So the idea is that the whole point of the bootkit is to let the kernel be unpacked in memory and get execution after, and patch the kernel on the fly. So if you're asking me like, can the operating system and can the kernel do it? Yeah, what I'm going to do basically is patch the kernel to inject those shellcode into it. So even if the kernel previously set it up, the MSR correctly and stuff, I can do it. Right? Make sense?
Yeah.
But good question, thank you. Any other question? All right. So if we put all those things together, we end up with a permanent lowering of the security level of any operating system. In particular, if you remove the CPU updates, like it's going to be system independent. If you remove NX, you get back to 97, because it's when like NX was first introduced. And I mean, it's a game changer in terms of security, right? Writing an exploit on a CPU which does support NX or doesn't is a game changer. There is one trick. There are two tricks actually. Even if your CPU does not support NX, you can still have non-executable pages. It can be emulated in software, stuff like PACs, for instance, protection against execution. And so this has to do with segmentation, and it's a lot trickier. The idea is that when you create an operating system, at some stage you will have to switch from real mode, which is 16-bit only, and like non-multitask, to 32-bit or 64-bit. To do that, you need to define a set of structures, like the global descriptor table, which contains the definition of each segment, assuming you're using segmentation. So if you're using segmentation, you're defining ranges of memory which have certain properties. So being executable, being writable, being readable. And you could actually change the, you could use the LGDT instruction to find the location of the GDT, then find the location of the segments and patch the permissions. But it's not such a good idea because the same bits have different meanings. If you set a code segment, it's never writable. And if you set a data segment, it's never supposed to be executable because the bit read and writable are the same bit. So if you flip it, it's not going to work too well. If you're using PAE, physical extensions, on 32-bit, it's even worse. And if you're using pages, I mean, it's going to be a bit of a problem because basically you cannot know the location of the pages you'd like to change permission from, unless you know the exact location in memory, in virtual memory. You can query the MMU and find back like where to patch in physical memory, but brute forcing every page is not doable given the size of the architecture. Was that very clear? Okay, so the idea that if we put all these features, even if you change your hard drive or remove the operating system, you're still very much going to be owned. And we don't even need like any other bootkit with a malicious payload. Any vulnerability to come, you're just going to be like bank vulnerable if you don't have an ASLR, if you don't have NX, and if you don't have SMM protection. I mean, it's Christmas time. It's a good question. I skipped that one. I forgot that one. I suggest you read the white paper. You'll be the one. Basically, for Windows, it's been identified by Kumar and Kumar where the seed for randomization is located. If you patch it with a static value, the mapping is going to be repeatable. If you think about it, for any operating system, the seed for randomization cannot come from user land. It has to come from kernel land. So if you patch the definition of this seed to be a static value, the mapping is going to be always the same thing. Yeah. Some people are paying attention. Thank you. Okay, the remote payload thing. We'll do some demos. Don't worry, it's coming. So the idea that even if today Coreboot is capable of bootkiting, say Windows 7 on 64-bit or 32-bit or whatever, Windows 8 is going to be coming. We don't have the final release, and we'd still like to be able to own it. Like if I take the pain to backdoor your computer today, I want to own you for the 3 years to come or something. So we definitely need a way to update, remove, or reflash the firmwares, which is going to be a lot trickier than expected. So if we only infect PCI firmwares and fetch the malicious code from the internet every time, we effectively don't leave any trace on the file system. The code we're going to put on the motherboard is not actually hostile per se. It's just like a slightly modified version of Coreboot. The file which is actually modified is a configuration file for IPXE, which tells it, all right, you're going to do an extension of a PXE boot, so boot from the internet. And the only parameter which is changing is basically like the URL you're going to boot from. So like to skip the magic, we're actually going to boot an operating system from the internet over HTTPS, and if possible over Wi-Fi. And there again, if there is no Wi-Fi, we default to Ethernet, DHCP, and if DHCP is not there, we can try a bunch of static IPs. Okay, I'll get back to the TrueCrypt problem. Okay. So in terms of portability, I think that using open source software to write a backdoor is actually a super cool idea. I mean, if I had to myself port stuff for 230 motherboards, I mean, a BIOS which is accepted by 230 motherboards, a lifetime would not be enough. So benefiting from the work of people who did like all the gory work of doing the hardware reverse engineering to get the portability done is just a massive help. The modularity of Coreboot is also awesome. You can put PCI firmwares, so a firmware controlling a CD-ROM. You can embed it directly inside the BIOS, which is not supposed to be. I mean, like, you give it like drivers for your network card, drivers for your CD-ROM, you make a single firmware out of it, you put it in your BIOS, and the BIOS is able to control everything without even requiring the help of the original firmware, which is located on the motherboard. So this modularity is very precious. And I explained that in terms of network stack, the fact of using IPXE is a massive help, because you don't have to recode yourself, say, an IP stack in real mode or in protected mode. So strictly speaking, the BIOS doesn't have to execute only in real mode. It can switch to protected mode. Provided it gets back to real mode when it gives back execution to the master boot record. And this is actually the trick that both Coreboot and IPXE are using, because it's a lot easier. You have proper multitasking. I mean, if you want to do a network stack, think about it. If you need a notion of timing without multitasking, is basically possible. You're going to wait for packets forever, or timeout or whatever. Implementing a timeout is just not possible without multitasking, I guess, unless you do something like waiting for physical interrupts, which is going to be super ugly and not reliable. All right, thank you for staying until now. We're going to do the magic demo of death. So that should be pretty interesting and show you how everything works. So let me check that I actually do have internet connection. Oh, sorry, Andrew. I meant Microsoft. All right. Seems like it works. Let me check if there is no like authentication with the over HTTP for. Yeah, no, it's cool. Okay, we have access to the internet, so I'm going to kill this stuff. I'm going to start a network sniffer to show you like what's really happening inside, because it's going to go pretty fast. Dear God. All right. So I'm going to sniff on any interface. Only HTTP is going to be really useful to us. Okay. the command I'm going to be using, so like I could show you on a proper motherboard, but it wouldn't be too visual. We could not sniff packets, etc. So we're going to use one of the motherboards, which is a virtual one, which is supported by Coreboot, and it's KVM, which is basically an extension of QEMU to benefit of kernel speed. So the thing is like this. We're going to just boot another BIOS instead of the normal KVM one, which is a Rakshasa.bin. Okay, we start in full screen, we need network, and the real disk we're actually booting is Windows 7. All right. Can I ask someone innocent to come and type my admin password? Andrew, do you know my admin password?
123 ABC.
How do you know?
Your friend.
Oh, come on. Can you please come over and type a password for me for the administrator account? What's the password? Well, that's the whole point, right? No, take the administrator one, which is like, I mean, are your privileges? Oh, you want that one? All right. Dude, you guessed it. Awesome, awesome. Can you redo it? Like, can you exit and log as a proper system administrator? Well, you removed my MSDN license, mate, so like... Okay, so it works too. Thank you for that.
No problem.
Wait until we look at the packets, come on. All right. Okay, so I'm just going to kill it. So let's look at what really happened in terms of HTTP connections. So first off, the BIOS itself tried to connect. I'm going to show you the configuration file later on to correlate this data. But like the BIOS itself tried to fetch a page which she's called like ads blah blah blah. It's a JPEG, but it's actually sending a bunch of .g parameters like an IP address, a MAC, and a gateway, which is a bit like suspicious. Normally this would go over HTTPS and there again over Wi-Fi. So in terms of forensic analysis from a network perspective, forget it. And this, so it's actually not an image, it's another IPXE configuration file. So the main configuration file, which is embedded in the firmware in the BIOS, is fetching another one from the internet because it's much easier to maintain. So it's telling him blah blah, so all this stuff is commented. It's telling him, all right, you're gonna fetch a kernel on an initRD, much like Linux really, from PMCMA, which is a website which is very much online. Okay, so let's go back to HTTP. This is the stuff in question. Alright, so it actually did fetch the stuff from pmcma.org. Here it's a mem disk, so it's like you have two parts. One is like a kernel, and the other one is like the payload itself. So this is a kernel which is really main disk, like just slightly modified, to boot the bootkit itself. And the bootkit, the proper bootkit is actually here, right? Okay, I'm going to show you the configuration file and we're going to trick it a bit. I won't have time to show you like even half of what I had prepared, but it doesn't matter. So let's look at this dodgy thing called love.jpg, which is very much the configuration file, right? It all makes sense. Just a bit of, I mean, we have to talk a bit of mitigations before I let you go. So I told you before that TPM is a passive ship, which means that if you have a bootkit and you're attacking a hard drive which is fully encrypted and stuff, if you don't want the data, you don't have to use a TPM. And it's not working, say, like game consoles, where the cryptographic chip embedding the cryptographic keys is actually active. And if you don't use it, the stuff just doesn't boot. So this is a bit of a problem. The main problem really when it comes to supply chain backdooring is that when someone delivers you a new laptop, he has not encrypted it for you, which would be also a problem. I mean, if they did, like, they would know your password, obviously. So, like, the thing is, they give you a laptop which is not encrypted, which means that TPM is actually not sealed, which means that TPM is actually not used. So TPM is not made to prevent this kind of attacks. How about antiviruses? I very much think that antiviruses, especially on servers, yeah, is a bit like putting lipstick. I know that many of you actually work for antiviruses, so I wanted to show you some love. Alright, this is the default Coreboot floppy, which is 3 years old, and I submitted it to VirusTotal. There again, this is the only piece of active malware, the stuff we're fetching over HTTPS and Wi-Fi every time when we boot. So detection ratio is 2/43. And if we pack it with LZMA, which is like the standard packer for the Linux kernel, for virtually every BIOS in the universe, the detection ratio is of 0. Other stuff you could do. So like if you own a machine, like because you got a remote shell, you could definitely flash the BIOS. You could definitely flash PCI firmwares. Well, there are limitations, but we don't have time for that. Another attack scenario could be, for instance, you purchase a new network card on eBay, and the stuff has been backdoored for you. And when you install it, you actually get home. You can even like backdoor data centers, because you can backdoor VMware. I haven't checked if it works with Hyper-V. Can you define your own firmware with Hyper-V? Not sure. All right, but it works with VMware. Remediation. So the main problem is that if someone puts a single rogue PCI firmware on your machine, he basically owns you forever. How many of you check your PCI firmware before using your first laptop? Bullshit. So I very much recommend to actually do it. Like when you get a new laptop, to flash all these dodgy firmware you don't understand and you cannot possibly understand because it's all proprietary. With open source stuff you can actually understand. So like Coreboot would be a good idea. It works on 230 motherboards. Yep.
Is your exploit kit configurable so that you could have it in exploit mode or in remediation mode?
There is a, so actually we can disinfect it, yes. All right, if I have one more minute, I will explain that. It's actually very interesting. The other point is like, after you get an intrusion, I mean, usually like the best practice is like restore for backup. Do you guys restore your firmwares from backup? And just the cost of doing this, because you cannot trust the kernel anymore, right? So like, if you got an intrusion like this, you would have to actually physically open your box and using a active FPGA, flash every single firmware on your board, including the BIOS and stuff. And since people never make backups of such things in first place, like I recommend to just throw your server away. It's going to be a lot cheaper than doing it actually and get the expertise to do it. So remote flashing, which was a very good question. Can you get rid of, I mean, can we disinfect Rakshasa? Or I told you that if I own one PCI firmware, which gets executed early, I can actually flash any other firmware, including the main BIOS usually. There is one problem with that. So the idea is that you can boot remotely an operating system. We've seen this. You could fetch a small Linux kernel with a small tool to flash the BIOS. And so like it's a floppy, you have a kernel, a tool to flash, a small bash script if you will, and the new firmware. This would be enough to flash the BIOS and possibly restore the original one or something which looks a lot like it. To flash another PCI device is actually a lot harder. In particular, we're going to see how to flash the network card. The problem with the network card is that tools to flash the network card are very much vendor dependent. So how do we go around this? In the network packets, we saw that the first stuff I was sending actually contain information such as my MAC address. And this is a feature of IPXC. If you look, it's not hard-coded. It's coded like this. Like you have net IP and MAC equals. All right, so it's a macro inside IPXC and it's very much fed dynamically. Yeah, I'm coming. So if I have the MAC address, I know the vendor because like I know the WIN number, and from the WIN number, I can use a vendor and send back as a payload a tool which is targeted to flash exactly this firmware for this vendor. It's actually supported by IPXC, so it's not a dirty trick. We don't have time, you sure? All right. Thank you for coming.